Okay, so it got disconnected. Okay. Sorry about that, it got disconnected again. Okay, so we were discussing this question. A rigid sphere of mass m, radius r, moves with a constant speed v through a dilute medium consisting of identical particles of mass m. The particles are initially at rest in the laboratory frame and have a uniform number density n, that is particle per unit volume. The particles do not interact with one another. Assume that each encounter between the sphere and the particle is perfectly elastic collision and that m is very much smaller than capital M. Determine the resulting drag force experienced by the sphere during these collisions. So this is the basic question. So we know that this, because every time there will be a collision between the sphere and this particle, there will be momentum that will be transferred from the sphere to the particle, and that will be resulting in the drag. Okay. So therefore, we need to find out two important parts here. First, how many particles hit the surface, hit the sphere per second, and second, how much momentum each particle gains. Okay, if we are able to solve these two things, we were able to find out the drag, because we are interested in mainly the momentum part. Okay. So first of all, let's find out how much particles hit the sphere per second. Okay. So we are going to find out how many particles hit the sphere per second. And so in time dt, the sphere moves, in time dt, small time interval, sphere moves distance, and that will be equal to its velocity multiplied by dt. Okay. So it means it sweeps out a cylinder of volume. Okay. So we can say that volume, or we can say that it sweeps out a cylinder of volume, and for that let us call this as in dV, and that dV will equal to area multiplied by the distance. So we can say that area is our pi r square, and that will be V times dt. And we can find out the number of particles in this volume. Say number of particles in this volume, and let us call this as d of n will be equal to over n multiplied by our pi r square v times dt, because we are given that this n is our particles per unit volume. Okay. And from here we can find out the collision per unit time. Collision per unit time, which is our dn by dt, and that will be equal to n pi r square multiplied by v. So we got the collision per unit volume. Now we come to our second part, and the second part we are supposed to, you can say, find out how much momentum each particle is going to gain. Okay. So we are going to find out momentum change of one particle. And in this particular case, what we are going to do, we are going to assume that the sphere, we are going to take the frame of reference as sphere, and we are going to assume that our sphere is at rest. So it means the particles are moving with the velocity v, not the sphere. That will be much more convenient. And for that, we are going to say that sphere's rest frame. Okay. So it means that our particles move with speed, and that speed is our v. Okay. And because sphere is very heavy, okay, so we can assume that the sphere will be always at rest. There is no recoil in the sphere, and the collisions are always elastic and frictionless. Okay. So it means that only because the velocity is going to have two components, one will be the parallel component, other one will be the perpendicular component. And we know that for elastic collision, where there is no friction, the parallel component remains unchanged, and it's the only perpendicular component that will be reversed. Okay, so we have to keep this in mind. Okay. And we can prove that also. Okay. And we can say that for elastic collision with a smooth wall, we can write that parallel component unchanged means velocity is parallel component. Parallel component is unchanged, and perpendicular component is reversed. Perpendicular component is reversed. Okay, that's a quite standard result. Okay, if we need, we can easily prove that also. Okay, we are going to write that V parallel is, that's quite simple, you can say, proof also. So we can write our parallel component will be our V sine of theta, and our perpendicular component will be our v cos of theta, okay, and that will be towards the wall. If initial speed is v and angle at which it is making theta is the angle with the normal, and from here we can write that our parallel component of the momentum, that is P parallel, will be equal to mv sine of theta, and we have our P perpendicular, that will be mv cos of theta. And we know that the parallel momentum cannot change, only the perpendicular momentum is going to change. Therefore, we can write that after collision, that P parallel prime is equal to P parallel, or we can say mv prime sine theta prime is equal to our mv sine of theta. And from conservation of energy, we can further write it as half m v prime square is equal to half m v square. So we get v prime is equal to v. Therefore, this mass and mass goes away, and because of this velocity, we can also cancel out this velocity. Therefore, we get sine of theta prime is equal to sine of theta. And from here, we can write that our theta prime is equal to pi minus theta. So this gives us that our direction is going to change. Okay, so this is the basic, we can say, direct relationship. And if we required, we can write there is equation also. So v parallel prime will be equal to v sine of theta, and perpendicular will be equal to minus v cos of theta. Okay, so this we proved that only the perpendicular component, the direction is going to flip its sign, that is change. Okay. And now we come back to our original portion, that is the momentum change in one particle. Okay. And we know that our perpendicular momentum will be equal to our mv cos of theta, and our parallel momentum will be equal to mv sine of theta. And like we said, the parallel component is unchanged, the perpendicular component is going to reverse its direction. Okay. Therefore, we can say that the change in momentum let us suppose that is our delta p of theta will be only because of the perpendicular. Okay. So we can write this as our mv cos of theta and minus of minus mv cos of theta. Therefore, we get that delta p of theta will be equal to about twice mv cos of theta. So we are able to find out the change in the momentum. Okay. Now here we are going to find out, you can say, we are going to introduce a new term here that is called as impact parameter. Okay. And many of you must have heard it previously also. Okay. That is quite common term in terms of the collision, and that is our impact parameter. And we are going to represent it as a B. Okay. And this impact parameter, it is quite easy to follow up. Suppose we are given a sphere and we have this is our center C, and suppose a particle is traveling and it strikes at point A, and if we extend this A further and draw a perpendicular between this, the line of travel of the particle, and join it to the center, this will be called as an impact parameter. Okay. And we know that this, if we join A and C, we are going to get radius. And all the particles, if they are between this B is less than R, okay, so they are going to actually hit the sphere. So we can write from here that for B less than equal to R, particles hit sphere. And if we extend this on the other side, let us suppose this angle is of theta, so this angle will be also theta. Okay. And from here we can also draw it in reverse. So we can say that if our B is greater than R, the particles miss the sphere. So therefore this is called as impact parameter B. Okay. And because of this triangle, let us suppose this is our point B. So in triangle ABC, we can find out a relationship between R and B. Okay. So we can say for triangle ABC, we can write that B is equal to R sine of theta. Okay. And so let us assume that we draw a circle with respect to this impact parameter. So this circle radius is our B, and let us assume that the thickness of this is our dB. So based on this, we can write this as our dA. So let us consider a ring of radius B and thickness dB. Consider a ring of radius B and thickness dB. Therefore, we can write area of the ring that is our dA will be equal to 2 pi B times dB. Okay. And we already know that our B is equal to R sine of theta. So from here we can find out our dB will be equal to R cos of theta d of theta. And we substitute here at dB. Therefore we get that our dA will be equal to 2 pi B times R cos of theta and R cos of theta and d theta. And if we substitute value of B also, we get this as our dA will be equal to 2 pi R square sine theta cos theta and d theta. So we are able to find out this small area dA. Now we are going to find out the average momentum transfer, because there are n number of particles that will be striking the sphere, and we will be rather not able to find out the exact value of the momentum that will be with respect to each particle. So we simply going to find out the average momentum transfer. Okay. Average momentum transfer, and let us call this a delta P, which will be equal to our total area and our area momentum with respect to our small area dP of theta, and this is our dA. And we simply substitute these two expressions and we get this as delta P will be equal to, we have this integration 0 to pi by 2, and we get this as 2 mv cos of theta. dA is our 2 pi r square sine theta cos theta d theta, and 0 to pi by 2 dA is our 2 pi r square sine theta cos theta d theta. And this 2 pi and 2 pi cancels out, and we also cancel out our r square, so we are left with 2 mv, and the respective the integration part 0 to pi by 2, and we have this as sine theta cos square theta. D theta, and 0 to pi by 2 sine theta cos of theta and d theta. Okay. Now it is quite easy, it is a simple integration. So our denominator will be giving us 1 by 2, and numerator will be giving us, so this comes as 1 by 2, and this will be coming as 1 by 3, and multiply by 2mv. Therefore we get that change in momentum will be equal to 4 by 3 m times v. Okay. Now we come to this basic definition of drag force, from which we started. So we can say our drag force, that is F, will be equal to rate of our striking this sphere and the momentum. Okay, we already have these two values, so we get F is equal to n pi r square v times 4 by 3 mv, and we can write this as F is equal to 4 by 3 pi n m r square v square, and this drag force will be in opposite side, so we can say this here F drag. So this is the formula for our, or equation for our drag force, because it will be acting in opposite direction of the motion. Go to the next question. Okay. It states that a ball is initially held at rest at a fixed point and then released. At the instant of release, an identical ball moving horizontally with the speed v collide elastically with it at same point. This is same, not some. Okay, this is same point. Determine the maximum horizontal distance traveled by the initial moving ball by the time it returns to the vertical height at which the collision occurred. So this question is a combination of our projectile motion as well as our conservation part. Okay. So we consider that, suppose there is a ball A and it is being struck by a ball B, and this ball B is moving in this direction and its velocity is given as v. Okay. And this ball, we already know that the ball B will be traveling this direction and ball A will be moving somewhere here. Okay. So it means the ball B, so if this is the level at which it is traveling, so this ball B is going to trace out somewhat a projectile, this path. Okay. So we have to find out the time it comes to the same vertical height. Okay. So this is a combination of our, you can say, conservation, collision as well as the projectile. Okay. So we have to remember that their masses are equal, collision elastic, and a ball is at rest. Okay, so we have to remember this part. Okay. And we are given that before collision, velocity of ball is given as v, and ball is our b, and velocity of identical ball, that is a, is 0. Velocity of ball a is equal to 0. Okay. And after collision, because we are only interested in ball b, so we are going to say that after collision, the velocity of ball b is supposed as u, and the angle with the horizontal it is making is suppose of theta. So ball b is moving with the velocity of u, and here we can, if required, we can prove, but we know from, you must have solved it many times, that the angle between the velocity of ball A and this velocity of ball B will be 90 degrees. Okay, if required, we can prove that. It's a quite simple derivation, and so let us sort it out. So we are going to use the conservation of momentum. And we know only initial ball B is moving, so we can say the initial momentum will be equal to mv in x direction, and our final momentum we can write this as our mass of velocity of B plus mass of velocity of our A. Okay. And conservation initial is equal to final, so we can write that our mv x unit vector should be equal to mb plus mva, which gives us that v is equal to vb plus va. Okay. And now we can use the conservation of energy. You can say our conservation of energy, and we can write that our initial half m v square is equal to half m u b square plus half m u a square, and this half m half cancels out, and this gives us that our v square is equal to ub square and ua square. Okay. And in terms of, let us suppose this is our equation number 1. So if we square equation number 1, squaring equation 1, we get that our ub plus ua whole square is equal to our v square, and we can just open the square. We can write this as our ub square plus ua square plus twice ub ua is equal to v square. Okay. And we know that our ub plus ua is equal to v square, so we substitute it here. We get the v square plus twice ub ua is equal to v square. These two terms cancels out, which gives us that our ub dot ua is equal to 0, or we can say that velocity of b is perpendicular to velocity of a. Okay. This relationship is quite standard, but we can anyways prove it. Okay. So this part was just the proof, nothing else is there in this part. We keep it as it is. Okay. But we are going to use this property, And like we said that, so for proving this, we assumed that the velocity of the ball was our ub, but actual velocity of the ball is our u. So we have to keep this in mind. Okay, so this part was only for the proof. So we know that our velocity of the ball b is our u. Sorry, u, 1 second. Yeah. And we can write that from here we can say its parallel component will be equal to over v cos of theta, and its perpendicular component will be equal to v sine of theta. Okay, that we are talking after the collision. Okay, we have to keep in mind this is velocity after the collision. Let me write it here. After collision for ball B. Okay. And here theta, we can say that theta is the angle the line of impact makes with the horizontal, and we know that after collision the ball B is going to lose its parallel component of the velocity to ball A. Okay. So we know that after collision the ball B loses its parallel component to ball A. So it means after collision the speed of ball B will be because of its perpendicular component, and that is equal to v sine of theta. Okay, and here let me correct one thing. This angle we are going to take as alpha, okay, because theta we have taken as the angle of the line of impact. Okay. And therefore we can say that the launch angle with respect to the horizontal is suppose our alpha, and that alpha will be equal to 90 minus theta. And from here, from our trigonometric, we can write that sine of theta will be giving us cos of alpha. Therefore we can say that our velocity of our ball will be equal to v cos of alpha. Okay, so this is the important part here. So we got the velocity of the ball is our v cos of alpha, because it is going to lose its perpendicular component to our ball A. Okay. And so now the velocity of a ball is our ub. So we can just draw specifically, because we are interested in only ball B. This is ball B, and it is going to be like a projectile. Its velocity is our u of B, so we can divide it into two components now. Okay. So we get this as ub of x, and this will be our ub of y. Angle of launch is given as alpha. So we can say that our ubx will be equal to our ub cos of alpha. So we get this as ub cos square alpha, and we have a u vertical component will be equal to our ub, and ub is our cos of alpha and our sine of alpha. And we know that our ub, this is v, not ub, because it is v cos of alpha. So it comes as our v, and this is also v. Okay. So now we come to the projectile motion of the ball B. Projectile motion of ball B, and its initial velocity in y direction we already know is our ub of y. So we can say the time to return to the same height, okay, or we can say in the for vertical motion, for vertical motion we are given that initial vertical speed is our u b of y. Therefore we can write time to return to same height will be equal to t, and that will be equal to 2vy divided by g, and this will be giving vy, we already know, this is equal to 2u of by and divided by g. So this gives us twice v cos alpha sin alpha divided by g. Now horizontal distance traveled during same time t. We can say horizontal distance is, suppose, our x of theta, that will be equal to our horizontal speed multiplied by time t, and we get this as our x of theta will be equal to our u bx, we know is our v cos square alpha, and this comes as our twice v cos alpha sin alpha by g, and therefore we get that the horizontal distance will be equal to twice v square upon g, and we get this as cos cube alpha, and we have this as sin of alpha, and we have to maximize, so we are only considering this trigonometric function. So for maximum distance, we are going to maximize f of theta, which f of theta we are going to take as cos cube theta and this will be in terms of alpha, not theta. So this is alpha, this is also our alpha, and this is also our alpha, cos cube alpha sin of alpha, and we are going to simply differentiate and equate equal to 0. So we can say df upon d theta, this will be giving us cos square alpha, and we have this as cos square alpha minus 3 sin square alpha, and equal to 0. So from here we get our tangent of alpha is equal to 1 upon square root of 3, which gives us that alpha is equal to over 30 degrees. Now this for launch angle, we are going to get maximum distance. Now we put this theta alpha as in the x equation in our this equation. So we get x of 30 will be our maximum is equal to 2v square upon g, and we have cos cube alpha. So this comes as 3 root cube and 1 by 2. So we get this as x of, there is no need at x of this. We can say our x maximum will be equal to 3 root 3 upon 8, and we get this as v square upon g. So this is maximum distance. Okay. So this was basically a combination of our conservation as well as the projectile whenever two bodies are going to collide with each other. Okay. Various parameters we can fix it and also find out. And we come to the next question, and it states that two identical fixed circle rings are placed in contact with each other, lie in a vertical plane. A small ball undergoes perfectly elastic collision as it bounces back and forth between the rings, as in the figure. Assume that initially conditions are chosen such that ball's trajectory always lie along a simple parabolic path. Let this parabolic intersect the rings at angle theta with respect to the horizontal. Show that in order to maximize the magnitude of change in the horizontal component of the ball's momentum at each collision, the angle theta, okay, so this should be theta, should be equal to square root of 5 minus 1 divided by 2. Basic figure is given to us. We have two rings and the ball is colliding between these 2 points. Okay, so let us call this as point P and this point Q. Okay, and sake of simplicity is also given that this path is parabolic. And initially it is given, let us suppose this angle, this we are having our center C, and here we are having center C prime. And for the sake of simplicity, let us assume that this is our origin. And if the circle are symmetrical, therefore we can say this is our minus r0 and this will be plus r0. These are the two coordinates of C as well as C prime. Okay. Therefore, we can find out the distance CP. So we can say that our CP will be equal to our r cos of theta and sine of theta. And therefore, the coordinate of P that will be equal to, this will be minus r0 plus r cos of theta and sine of theta. And therefore, we can write the coordinate of this P will be equal to, this will be minus r plus r cos of theta, and we have this as our r sine of theta. Okay, and symmetrically there will be also the coordinate of our Q. Okay. And we can similarly write, the coordinate of Q will equal to plus r minus r cos of theta and r sine of theta. So this will be our coordinate of Q. Okay. Next, we are interested mainly in the x coordinate, and then we can, because we are going to find out this distance between the two. Okay, it means we have to find out PQ, and for that we are required the x coordinate. Okay, and from here we can say that our Px is equal to minus r plus r cos of theta, and we have qx is equal to plus r minus r cos of theta. And let us suppose the horizontal distance between P and Q is given as x. Therefore, we can say that our x is equal to qx minus px. Okay, so we get this as r minus r cos of theta and minus r plus r cos of theta. So we get that our x will be equal to minus is plus, so this comes as our 2r, and this will be minus, this will be also minus, so 2r we can take as common, so this will be 1 minus cos of theta. So this is the distance between the 2 points P and Q. And if you look closely, if we say that the point of launch is our P and the landing point is Q, so this PQ is nothing but our range of the projectile. Okay, because in the question it is mentioned that it is having a parabolic path. Okay, so we can take that this as a projectile. So it is going to launch from point P and land at point A, or vice versa also, but we are going to consider only one direction. So this x will be nothing but our range of the projectile. So we are going to find out this range of our projectile. And so let us consider point P and point Q. We are launching a project from point P with the velocity v, and let us suppose angle is theta. Okay, and this distance is also over x. Okay, and it is going to land at Q. Therefore, we can say the horizontal range is that is x is equal to v square upon g and sine of 2 theta. That is our standard relationship. Okay, and we can equate both equation 1 and equation 2. So we can say from 1 and 2 we get this as our v square upon g sine 2 theta is equal to 2r 1 minus cos theta. And so we can further write it as v square is equal to, we can take this sine theta, 2 theta is 2 sine theta cos theta, so 2 and 2 goes away, so we get this as our gr 1 minus cos theta divided by sine theta and cos theta. Okay. And we know that our horizontal speed is our Vx is equal to V cos of theta, and let us square it, so we get Vx square is equal to V square cos square theta. And in place of V square we simply substitute our value, so we get this as our Vx square is equal to, we have this as gr 1 minus cos theta cos square theta and divided by sine theta cos theta. And